Welcome back to the Molecular Mind with AS. Today we're re-diving into an exciting concept from Chapter 6, Equilibrium. And we'll explore how pressure affects the position of equilibrium in gaseous reactions. So, get ready to understand how increasing or decreasing pressure can actually control the direction of a reaction. Let's begin with a simple idea. When a reaction reaches dynamic equilibrium, it means the forward and reverse reactions are occurring at the same rate. But what happens if we change the pressure on a system containing gases? According to Chatellier's principle, if any change is made to a system at equilibrium, the system will adjust itself to counteract that change and restore equilibrium. According to Chatellier's principle, if any change is made to a system at equilibrium, the system will adjust itself to counteract that change and restore equilibrium. So, when pressure changes, the equilibrium will shift in a direction that helps to minimize that pressure change. It's like a chemical balancing act. And today, we're putting a thumb on the scale to see what happens. Now, the effect of pressure only matters in gaseous reactions because gases have volume and can be compressed or expanded. Solids and liquids, not so much. Let's take a famous example to make this crystal clear: the Haber process, where ammonia, or NH3, is produced from nitrogen, N2, and hydrogen, H2. The balanced chemical equation looks like this. N2 gas plus 3H2 gas is in equilibrium with 2NH3 gas. Take a close look here. On the reactant side, we have 4 moles of gas. That's 1 mole of nitrogen plus 3 moles of hydrogen. On the product side, there are only 2 moles of gas, which is 2 moles of ammonia. This difference in the number of moles is the key. Now imagine this system is at equilibrium inside a closed container. If we suddenly increase the pressure, say by pushing down a piston, the system will try to reduce it. How can it do that? By shifting the equilibrium to the side where there are fewer gas molecules, because fewer molecules will exert less pressure. In our Haber process example, the product side has only 2 moles, while the reactant side has 4. So, the reaction moves in the forward direction, producing more ammonia, NH3. That's exactly why the formation of ammonia gas is favored at high pressure. We're literally squeezing the reactants together to form the product. But what if we do the opposite and decrease the pressure, maybe by expanding the container? The system will again try to counteract this change by increasing the pressure. It does this by shifting to the side with more gas molecules. In this case, that's the backward direction, breaking down ammonia to form more nitrogen and hydrogen. So, lower pressure decreases the ammonia yield, while high pressure increases it. However, it's a balancing act in the real world too. Extremely high pressures can be expensive and dangerous to maintain. That's why in industrial settings, a moderately high pressure of around 200 atmospheres is used to get an efficient and economical yield. Let's quickly summarize what we've learned. First, pressure changes only affect equilibria that involve gases. Second, if you increase the pressure, the equilibrium will shift to the side with fewer moles of gas. Third, if you decrease the pressure, it shifts to the side with more moles of gas. And finally, in the Haber process, this means high pressure is our friend for making more ammonia. So that's how pressure can control a chemical equilibrium. And it's how we produce something as important as ammonia, which is used to make fertilizers for the crops that feed us. If you found this explanation helpful, don't forget to like, share, and subscribe to the Molecular Mind with AS for more chemistry made simple. And let me know in the comments below, which factor do you want me to explain next? Temperature or catalysts? See you in the next video.